All good, Leo? We're broadcasting.
All good.
Okay. So welcome back, everybody. To our Tuesday session. I'm losing track of the days, but I think it's Tuesday. So we have another great set of lectures planned today, and we have a new lecturer today. So let me briefly just introduce Ehud Altman, who is doing a lot of the leading work on true far from equilibrium dynamics. He received his PhD from the Technion and then did a postdoc at Harvard before being faculty at the Weizmann Institute and then moving to Berkeley several years ago. And he has broad-ranging interest in non-equilibrium and condensed matter and ultracold matter, but I think really his primary focus has been on really truly genuinely new non-equilibrium phenomena, things like scrambling and these circuit transitions recently, thermalization and the lack thereof, which I think is one of the big things we're going to hear about today. And so you'll have time to interact and ask him lots of questions about all these topics, but without any further delays, why don't I turn it over to you, Ehud?
Thank you, Kaden. Thank you for inviting me to give a talk, to give a set of lectures in the school. I really remember the school fondly. I organized it actually once, even when I was a postdoc, and it was really a lot of fun on location. So I'm a bit sorry that I can't be on location. So I'm going to give a set of 3 lectures. My first one is going to concentrate on many-body localization, and it might take 1.5 lectures. I want to go slowly so people can follow and ask questions. The other half of my lecture set will be on scrambling and dynamics of quantum information, with a focus on quantum circuits, random quantum circuits. But today I'm going to talk about MBL, and I looked at David's lecture notes. I sort of going to, he went slowly and thoroughly, so I'm going to take advantage of that. I'm also going to go slowly, but I'm not going to have too much overlap with him. I want to be a bit complementary. The first part of my MBL lectures will be focused on the MBL transition. I'll talk about the RG framework, how today we see it and think about the MBL transition. I'm not going to be heavy on microscopic RG framework, but really talk about the qualitative and things we can understand from the philosophy of the RG. And then I'm going to take advantage of this approach and use it to develop a 2-parameter scaling theory that now I think people believe is more or less the state of the art of what people, what we think about this transition, many-body localization transition. Then I'm going, in the second part of today's lecture, I'll see how many-body localization can be seen even in open systems, which is somewhat non-intuitive and is based on work with Zala Lenarcic and Achim Rosh. Okay, so let me start with the first part. If you remember from David's lectures, if you've been to David's lectures, basic Hamiltonians we're looking at, and I'll mainly consider one dimension here, is a chain of spins, for example, with on-site disorder. This is the first term, H naught here. Let me, maybe actually, is there a way to, there is a way to, okay. So there is, H naught is on-site disorder, and then there is coupling between the spins, which we'll take to be nearest neighbor of very short range. And this is the V term here, or J term. So an example of such a term could be just say a Heisenberg term plus maybe some transverse field that breaks the SU2 symmetry.
You don't mean the commutator by those brackets, right? You just
Oh, no,
mean
no. Sorry, this was really bad notation. Sorry, maybe I should. No, this is not a commutator. Yeah, this was really, it was supposed to be a function of these spins. Okay, so what is a basic criterion for localization in a system of size L? So as a basic criterion for localization, we can ask, suppose we have only H naught, and we take an eigenstate of H naught, we can ask the question whether this eigenstate can decay by applying the perturbation J, the coupling J, whether it can lead to decay of this eigenstate into the quasi-continuum made of all the other eigenstates of H naught. Okay, so let's try to understand the criterion for this. So if I look at the eigenstate of H, a typical eigenstate of H naught seen here, right? This is a typical eigenstate of H naught. Let's see if it can decay to other eigenstates. Other nearby eigenstates of H naught will typically have very different configuration of spins with order L different spins. So of course we cannot flip them with first order process in J. We need a very high order process. So there is, we need to go to Fermi golden rule at very high order in this framework. And typically we'll have to go to order L, which means that the matrix element will be exponentially small in the system size. And this is what appears here. This matrix element is exponentially small, and the length scale that controls this exponential decay of the matrix element, let me call it a localization length. Okay, this is the matrix element, and to get a rate, we need the density of states, which is simply 1 over the many-body level spacing, which is the bandwidth over 2 to the L. Okay, so this is the rate at which, if Fermi golden rule worked, the state would decay. But of course, it doesn't. We're not guaranteed that Fermi golden rule will work, because for Fermi golden rule we need a continuum, and the criterion for an actual decay is that the broadening of the level that we just calculated is larger than the level spacing, which then renders this these levels as a quasi-continuum, as you know, at least as far as this decay is concerned, if this ratio is much larger than 1. So now sticking in this, what we have here, and the level spacing, we see that the decay rate, or broadening of the level over the level spacing, behaves like this, e to the minus L over xi minus L times log 2 because of the denominator, because of the level spacing. We find some kind of an interesting thing that there is a minimal localization length. If the localization length is larger than 1 over log 2, then this will not be a decay. It will be this G, which serves as our criterion, will at sufficiently long length scales will become enormous, right? It will grow exponentially. So there seems to be a minimal localization length. Here, I made a very kind of rough criterion using high order Fermi golden rule. There is a nicer way to formulate this criterion, which I give you as an exercise. So, until tomorrow's lecture, maybe you can look at this exercise, how to formulate this criterion in a different perspective, the perspectives of the L-bit Hamiltonian, the effective Hamiltonian in terms of the local integrals of motion that David talked about in his talk. So this is basically an exercise. I'll leave the notes on the site so you can do it. But the main thing is you'll get the same thing. And what we find here seems a bit strange. It looks like the localization length jumps across the transition. Basically, there is a minimal localization length in the MBL phase, and of course, it's infinite once we go to the delocalized phase. So does that mean that there is first order transition, no diverging scale, no scale invariance at the critical point? Well, not necessarily. We'll see that if we use this criterion judiciously inside an RG scheme, it does yield a critical fixed point with scale invariance. So let's see. I'll just talk in a few minutes about how, in principle, one can think about it, and then I'll look at two simple limits. So there's been several papers about different variants of the RG scheme. Since I'm kind of qualitative, let me just talk broadly. And this is, I think, one of the first papers was by my student Ronen Vosk, David Hughes, and myself. And the idea there is that what we did here in formulating the criterion was a bit cavalier, because we assumed that this parameter G, the ratio that determined whether the system is thermalizing or localized, is uniform throughout the sample. But we know that when we get close to the transition, even in statistical mechanics, we have puddles of the two phases inside the system, and they compete with each other. So we think of the sample close to the MBL transition in the same way as having regions that basically behave like thermal phases locally, and ones that behave as insulators. And that depends on this kind of local ratio between a matrix element to basically just couple the spins inside this region over the level spacing this region would have if it was on its own. And then in the paper, we derived an RG scheme to gradually merge these regions together if they thermalize at some running cutoff scale of time. So if they thermalize each other, then they're made into a single block and so on. And here I'm not going to talk about the specific rules. I think for now they're not so important. We'll see that we can derive phenomenological scaling equations by simpler considerations that it turns out agree pretty well with these more microscopic rules. So in order to get to that, I want to talk about two interesting limits. I want to talk about the nature of rare inclusions that behave like many-body localized regions locally inside the thermal phase. There is always some chance, because we have random disorder, there is always some chance that we'll have such a region. And the question is, what are the consequences of having these? And two, I want to talk about the dual scenario, which is rare thermal regions inside the MBL phase. Are there any questions, by the way? Don't hesitate to ask in the middle. It's,
Is there something related to like Kibble-Zurek when you mentioned that different regions?
Yeah, well, okay, so Kibble-Zurek is a mechanism where you have different regions and you generate them dynamically because you go through the transition and the system doesn't have time to relax. But even if you don't talk about Kibble-Zurek mechanism, so I'm talking about really not doing anything dynamical. Even if you talk about, the simplest thing in statistical mechanics, graduate statistical mechanics, you learn about the Ising model. You can see pictures of how it looks. You can run a Metropolis algorithm and see how the Ising model looks by time step after time step in the two sides of the transition, and you see that if you're in the ordered phase, for example, you'll find that you have majority spins, but there is growing and growing regions that have the opposite spin, right? So, and if you're in the in the high temperature phase, there is a growing correlation length, and how it looks in pictures is that you see larger and larger regions that actually look ordered inside the disordered phase. Okay, so it's really much more standard than Kibble-Zurich. It's like any other phase transition, you expect to see pedals of the other phase, minority, but some pedals like that. Now, the fact that this is not equilibrium is important here in the sense that we'll see that if we have a thermal region in the MBL phase, it causes an instability. Actually, David talked about this, so I'm going to briefly remind you, but I'll remind you, and then I'll use this. I'll take advantage of this to build a scaling analysis. Yeah. Anyway, so now I'm talking about the rare regions that are many-body localized. If I'll isolate this region by itself and do numerics on the disorder we find there, it'll look MBL-like. And you could think about it microscopically as we have disorder in the system. The disorder is random. It's not large enough to give us localization, but by chance we can get regions where the disorder is slightly bigger than you would expect, right, on average. So it's enough to take you to the other side of the transition, but only in a finite region, right? So you always have some probability of finding such regions where the disorder is larger. Of course, to find a larger and larger region like that would be exponentially rare in the size of the region. And this is what this probability distribution is telling you. So basically the occurrence probability or density of these minority regions of size L goes like e to the minus L over xi. And if we're close to the MBL critical point, then we postulate that there is a critical point, and then at the critical point, there is a diverging length scale. And as we approach the critical point, this is the only important scale that determines these this probability distribution. So by basically assuming this second order transition, that probability distribution, the probability of having a large thermal block of size L goes like this. So in a one-dimensional system, that the transport or the thermalization, if you want the thermalization, even if we don't have transport, the thermalization of a system of size L is bottlenecked by the thermalization through this MBL region. So in order to determine the thermalization time, we can try to assess what is the time scale for thermalizing this, the largest region that we expect to find in our system, right? So although these regions are rare, if we look at sufficiently large system, we can find regions that are as large as we want, right? So say we have our total system length is L, what is the region that, the largest region that we'll typically find? Namely, what is the region that has probability 1, order 1 to find in a system of size L, where it's clear, right? If the density of regions is this, then the probability in a system of size L is equal to probability of finding a region of size larger than L is equal to L times rho L, right? big L times rho small l, and we want that to be 1. And that will be the largest, let's call it L thermal. That will be the largest thermal block that will control the thermalization, non-thermal block. We call it L thermal, but it's confusing. It's the largest MBL block. It controls the thermalization time. And so now we can plug it into this, and we see that the largest block we'll typically find is order log of L, right? So important thing here is that psi goes like psi times log of L. Sorry, L of L thermal. Okay, that's the only important thing to understand here, right? That the largest thermal block typically goes like log of the system size. So now we can say, what is the thermalization time? Well, this block has some localization length, L naught, which is a microscopic scale. And the time scale it takes to thermalize across it is some microscopic time, tau, time exponentially long in the size of this thermal, this localized region over the localization length. So it's, so now plugging in LTH here, we get that tau goes like the system size to power psi over L naught, where I remind you psi is the correlation length. Psi is the correlation length. So the upshot from all this is actually quite interesting. We find a relation between the time scale for thermalizing and the system size. So the relation is tau goes like L to the power psi over L naught. That defines dynamical scaling relation, right? Scaling relation between length and time is a dynamical scaling relation, and the dynamical exponent, the exponent that appears here is called the dynamical exponent. It's called Z. And in this case, Z is equal to psi over L naught. L naught is some microscopic localization length in the MBL region, and psi is a diverging scale. It's a diverging correlation length. So we see that the dynamical exponent diverges at the critical point together with the correlation length. That's one important thing. Second important thing is that the transport now is not diffusive, but it's very strongly subdiffusive. Here there is some remark I may need to make. The time scale I wrote here, tau, is not a time scale associated with relaxation of some hydrodynamic quantity like the total particle number. If I need to relax the total particle number across this, this bottleneck, I have, say, n particles here and well, n particles more here than on the other side. I have to transfer about n over 2 particles in order to completely relax this density imbalance between the two sides, right? So, so that the time scale for relaxation of hydrodynamic quantities like density or energy is order L times tau, times the tau I had here. So the transport relaxation time, tau transport, is equal to L to the power psi over L plus 1 because of this. So that's it's not so important as you see close to the critical point because Z diverges. So this plus 1 becomes not so important, but it's just a thing one needs to understand. In any case, what it tells you is that the relaxation of conserved quantities like energy or particle number is very different than what you expect in diffusive systems. In diffusive systems, you have diffusion, and in diffusion, you know, the length, the size of a diffusing blob say, let's call it L, or let's call it L, goes like the time, like square root of the time times a diffusion constant, or if you want, tau goes like L squared, right? So Z equals 2 in diffusion, while in our case, we have Z that's huge, and that's called very super diffusive. And at the critical point, exactly, Z goes to infinity. So everything sort of almost stops.
Ehud, if
Yes.
I just had a normal liquid or something, how are the transport Z and the normal Z related? Is it the same, or is it, are they, you know?
Yeah, yes, in principle, yeah, they're related in the same way. Usually you'd have, if for non-conserved operators will be ballistic, like the Lieb-Robinson bound allows them to be. So if they're not bound by conservation laws, they'll propagate ballistically. So correlation functions of non-conserved quantities will go much faster than correlation functions of conserved quantities. So we'll talk about it a little bit next time when I talk about scrambling. Okay, yeah, but you're right.
So that's kind of a case where Z would be 1 and Z transport would be 2.
Yes, exactly, right. So in general, yeah, we'll talk about butterfly velocity and all that, and that's sort of related with how, you know, generic operators grow ballistically with some constant velocity, and that Z equals 1, because time and size are proportional to each other, and length are proportional to each other. Yeah, so that's pretty general. That's right.
And that would be true even in this, you know, take a simple case like a dilute Bose gas where Z is equal to 2 near the sort of vacuum transition.
Yeah, but this is right. This is a different Z equals 2 because it's a non-dissipative. There is no transport, dissipative transport. It's basically Galilean invariant situation. So there, it's not going to work. Right. So this works for really relaxation and scrambling versus and relaxation. In such a Galilean invariant system, there isn't really relaxation. So I don't think that will work. Good. Yeah. So one remark is that what I talked about here, these bottleneck effects are very special to D equals 1. And I invite you to think about what, you know, if you had a localization transition in larger dimensions, how it would look like. In principle, we expect their diffusive transport, which is, you know, from hydrodynamics, we expect diffusion, and there is no reason why it will not continue all the way to the critical point. And there, maybe at the critical point, you'll get a different dynamical exponent. But all the way to the critical point, you can get diffusion. And the way you will see the transition is that the diffusion constant D is going to vanish at the critical point. That's the general thing you would expect in higher dimensions. And the reason is that that there are no bottlenecks in higher dimensions. So if you have an insulating region, you don't have to go through it. You can go around it and you can short it, right? Here, you cannot short it. All the transport, if you want, is in series. Okay, so here I give you an exercise that you will have to think about. I'll just tell you what it is. Here I talked about thermalization and I talked about transport of conserved quantities. There is a concrete experiment done in Emmanuel's Bloch group where they observed, maybe Emmanuel will talk about it next week, where they observed a decay of a density wave. So they start with a density wave in the initial state. The initial state has, say, for example, 1 particle, 0 particles, 1 particle, 0 particles, and so on. In consecutive sites. This is, for example, a paper you can look, and then they look at the decay of this density wave, and you know, you expect it to decay in the thermal phase to 0 because there is no density wave in the equilibrium of that system, and it does not decay in the MBL phase. But if you go close to the MBL phase, what you expect, well, with the remark that maybe I have to remark that in these experiments, I cannot use the kind of arguments I used here because it's not really a random system. But if it was a random system, what would we expect? And I want you to show that in this Griffith phase, in this, because of these bottleneck effects, the density wave decays as 1 over t to the power minus 1 over z at long times. So that is what I want you to try to find for yourself. And you can, well, yeah, if you want help in that, you can, I give a hint here and you can ask me more.
So Ehud, I have a couple questions on
Sure.
these remarks. So the first about decaying exponentially. So I agree that is, if I just think about like the hydrodynamic theory, what I would expect.
Yeah.
But the reason I'm trying to reconcile this with another hydrodynamic theory where I know it goes like e to the minus t cubed. And this is, so there are experiments done in cold atoms, like by Joseph Tywison, where they just put a spin spiral, for example.
Oh, I made a mistake here. Sorry, t dq squared here. Sorry, it's times dq squared. Yeah, sorry. Yes. Yeah.
Oh, yeah, sure. And so there you don't get e to the minus t, but you get e to the minus t cubed. So is the reason just that it's a different hydrodynamic theory? It has a different symmetry or something?
Sorry, in which case it goes like t cubed?
So
maybe at very short times it goes like t cubed, right? T squared or...
No. It's not the simple perturbative short time that I'm thinking.
Oh, in which case? Oh, are you talking about Galilean invariant?
This again may be a case of a Galilean.
Oh yeah. So right.
The experiments are not. They have a trap, but I guess maybe the hydrodynamic theory they're using is Galilean invariant, since there's no disorder or anything.
Right. So it's true that in Galilean invariant systems, there is no hydrodynamic theory is different. There is no hydrodynamics is singular. So there are a lot of problems with hydrodynamics in 1D, and in 1D Galilean invariant system, it's singular, and what you get actually is a KPZ universality class for decay of for decay of correlation functions. So there is a different universality class, for example, for Gross-Pitaevsky equation and decay of right, that finite temperature Gross-Pitaevsky equation will give you in one dimension will give you a different decay exponent. That's true, right? So here I'm talking about a generic, but if you add some disorder and break Galilean invariance, then you will go back to usual diffusion. And actually, that's also true in spin systems. So in certain, there is now a lot of interest in integrable but non-interacting quantum spin chains like Heisenberg spin chains, and they're supposed to also show KPZ universality class, at least numerics shows, and there are some arguments but not complete understanding of that for Heisenberg integrable Heisenberg models, and there was just a very nice experiment by Emmanuel Bloch showing that. So diffusion, we know, is not completely guaranteed, especially in one dimension. And I think the consensus is that the Heisenberg model, even for spin 1 or higher spins where it's not integrable, it should behave diffusively eventually. But there are indications that for a very long time, it looks like KPZ, and it will revert to diffusion after a very long time. And I think it has some relation to this issue of Galilean invariance, because if you look at the band edges in this case, which determine maybe the long time behavior, the band edges in a fair, or the top of the band corresponds to it. So if you take Heisenberg model, it looks like even if it's an antiferromagnet, the highest energy states behave like the states that spin waves of a ferromagnet, and the spin waves of a ferromagnet have Galilean, effective Galilean invariance. So it might be related to that, although that would be more general than having just spin half. So you also need the integrability to get this behavior.
Yeah, so the systems I was specifically thinking of, I think, are very different than this KPZ story, but I do think the Galilean invariance is probably why the theory is.
So which systems again?
It's just a strongly interacting Fermi gas with spin 1/2, and so they put in sort of magnetization waves. There's also an SU2 symmetry, which you have to be careful with.
Is it in 1D?
These are, well, the experiments I'm thinking of are 3D.
Okay, so 3D and not getting diffusion is pretty rare, unless you're
Yeah, I mean, so maybe if we have time in the comments, I will continue to push on it just because I think it's interesting, but I don't want to distract you. Because I don't think it's key to what you're talking about. I did want to ask, you've used this phrase Griffith's phenomena a few times.
Yeah.
And I guess, I understand that in the traditional equilibrium Griffiths effect, there are these rare regions and things. Is there a deeper connection there? Like, naively, the Griffiths physics seems quite different from the MBL physics, but are you just using it because of the rare regions? Or
it's not very different, actually. Yeah, it's both. It's rare regions, and when people talk about Griffiths phenomena, it's usually only seen in dynamics. It's not seen in thermodynamics. So it has to do with the fact that you have broad distribution of relaxation rates. And
for example,
this is exactly
I don't have
what
a
is happening here. You have if you look at the distribution of relaxation rates, you'll see that you have a power law distribution of relaxation rates, or a power law distribution of relaxation times. So it's very similar to Griffith effects. There you essentially almost the same in Griffith physics of spin chain, in spin chains and spin systems. The dynamic susceptibility is affected by the averages are affected by rare regions that take a very long time to respond. And that's exactly what is happening here. So I think it's basically the same phenomenon. Yeah.
Thanks.
So, yeah. Okay, so I talked about rare MBL regions in the thermal phase, and now the question of what happens if I have a thermal region in the inside the MBL phase. And I think David talked about this, so I'll be very brief. I'll just remind you that there is a paper by Duroc and Huveniers and a lot of follow-ups that show that there can be a special instability called an avalanche instability triggered by having such a region. And the idea is, briefly, is very, very simple. Suppose I have this thermal region. It can serve as like a mini bath to absorb and thermalize nearby spins. If I think of an L-bit picture, I have L-bits here. Now I take this region and bring it close and connect it to the L-bits. I can ask how far it can go and thermalize. So suppose, of course, it can easily thermalize things nearby it. Suppose it could thermalize all the way to radius r. Would it be able to thermalize the next spin? And again, the sort of arguments are very similar to what we did before. We ask about the matrix element coupling between our L-bit and this region R away from it. And this matrix element decays like exponentially, like e to the minus L over 2 xi, xi localization length, times some microscopic coupling, J. And there is a factor of 1 over square root of the Hilbert space dimension, just because we're coupling to a bath, so we're coupling to delocalized states in Hilbert space, and this is a normalization factor for the eigenstates, right? So when we have calculate the matrix element, right, we have to take into account the normalization factor. just as in usual Fermi golden rule, when we couple to a delocalized state, we have a 1 over square root of L. So this is the matrix element. Now this is the level space. If we said that the our first L bits were absorbed into the bath. So if they're absorbed into the bath has a level spacing of the bandwidth over 2 to the L plus R, right? So now we have this criterion that we had before G, the resonance condition, basically the matrix element over the level spacing or the decay rate over the level spacing, it's the same thing. And we get similar to what we had before. Again, we see that there is a criterion that there is an instability that you can thermalize more and more spins, more and more L bits, if your localization length in the many-body localized region is larger than 1 over log 2. And if you generalize this to higher dimensions, you can easily see there the matrix element still goes like the distance, but the level spacing goes like the volume of the region that you've just thermalized. So it's much more severe against the possibility of localization, and you'll never be able to localize because then you'll be fighting an exponential decay with a Gaussian decay, right? So there is, according to this argument, many-body localization will always be unstable in higher than one dimension, and in 1 dimension, it's unstable if the localization length is larger than log 2, 1 over log 2. So I want to point out that this is in sharp contrast with the original perturbative argument by Basco, Alainer, and Altschuler, which basically, if I take, they look perturbatively near a non-interacting Anderson localized phase and ask the question whether the system will be stable to introduction of a weak interaction between the electrons. And the way they thought about it is very different from this. Well, similar in the sense that they looked for resonance, but they were perturbative in the interaction strength U. So by acting with a single interaction, right, what you can ask whether you can decay into a multitude of particle hole excitations that you can create with an interaction, right? The interaction looks like this, U times C dagger alpha, C dagger beta, C gamma delta. So it's a 4 fermion term. Alpha, beta, gamma, delta are orbitals. I have to sum over orbitals. But the question is, given suppose I'm in some state of the non-interacting system, can I decay into many particle hole excitations by using the interaction? And the criterion for this is basically proportional to the interaction strength times the number of decay channels. I won't go over it. You can, I leave it for you to look at as maybe an exercise to see if you can rederive it. It's actually simple Fermi golden rule analysis, but then you find that the critical interaction strength in this case goes like 1 over psi localization squared. So if I plot the interaction strength versus the disorder strength, which you can think of as 1 over the localization length, then the Basco, Alainer, Altschuler criterion looks like the red line here, which means that everything above this line is delocalized. But below this line, the interaction is not enough in order to fulfill Fermi golden rule and allow decay in this regime. So this regime is perturbatively stable according to this perturbative criterion, but according to the non-perturbative criterion by Deroik and Houdinier, this is not true. If the non-interacting localization length is larger than 1 over log 2, sorry, yes. Sorry, I made a mistake here. This is log 2 here. if 1 over the localization length is larger than log 2, then we're stable. But if not, we're unstable. So this is, even in 1 dimension, there is a big difference from the original criterion.
In this DRH criterion, this blue line you drew, so I understand where the point at log 2 comes from, but is the line, are you just kind of sketching that by hand?
Yeah. The line, I'm just sketching how it would be. You can imagine that it would go that way, because if you have a finite sufficiently strong interaction, the interaction starts to act as a delocalizing effect, right? Because it can transfer you between orbitals. So the localization length will self-consistently change, and then you'll change the criterion. Okay, so it should go this way. How exactly is hard to calculate.
But log 2 is in the non-interacting analysis?
Oh yeah, the log 2 is very general. Yeah, so the log 2, oh, sorry. Good point. Let's see. So,
like in your rare regions.
Yeah. You could, that's right. So this log 2, first of all, it's not completely a universal thing if you can, right. So, yeah, that's right. So let me say it that way. But I'll show in a minute why it's not really a universal thing. So it could be higher. The true localization length could be higher, and then you have some renormalized localization length that will be log 2 at the transition. So what has to be, so all of what we, all the criteria we did now were not dressed with RG, so they're actually kind of microscopic criteria. And when I say that it's log 2, I didn't take into account the fact that the localization length can be somehow renormalized by interactions, and then the renormalized thing would be log 2. So in fact, if this is sort of a just a perturbative localization length, I would say this is sort of a, maybe I should write here disorder strength. Okay. This is just disorder strength. And this is the point where the local, where psi naught is equal to log 2. Maybe that's a better thing to say, because localization length is not well-defined concept. In the end, the localization length will be renormalized after when we look at long distances and over a very inhomogeneous system. So yeah, thanks for the question, because I think that was not very accurate. So this is disorder strength, and this is the disorder strength that gives you exactly localization length of log 2 as a non-interacting system.
Can I ask a question?
Yeah.
Do we expect some sort of different dynamical behaviors in the delocalized regime and the perturbatively localized regime? As we cross the red line, should there be some slower transport?
Inside the delocalized regime, I think qualitatively it sufficiently short times, certainly, yes. Yeah, but because these non-perturbative processes also take a very long time to develop. So it could be that this is all you have a chance to see in reasonable timescales in experiments. It's a very good question. I do think that actually these non-perturbative arguments are correct, and there is a lot of numerical evidence that they work. I actually initially did not believe them, and then I did numerics and saw that they actually work. That in particular, this criterion, the fact that in 1D you have a sharp instability is a pretty striking prediction, which actually checks out. But I think if you look at short times, then there will certainly be a crossover in this BAA criterion.
So Ehud, and I think this is related to Francisco's question that so when David at the end of his lectures, he had sort of tried to sketch picture, there's this asymptotic, the true MBL transition, and then there's the MBL crossover. And if I understood sort of his claim and maybe what you're saying correctly, this red line might correspond to the sort of crossover, what you'd probably
okay, no, I think what David talked about is another layer of complexity that I didn't want to get into, and which I think is not well understood. There is a recent paper by David, but the fact is that this avalanche instability is not the only kind of process inside that makes the MBL phase not completely localized. So this there are two things that can happen. You could have these regions that are MBL-like, which there are thermal regions, and what I call thermal regions are regions that where a macroscopic number of states are mixed with each other, and they're completely delocalized in this way. On the other hand, there can be also another kind of resonance where just two states, for example, or just three states are mixed with each other. And that's not a macroscopic resonance, but and there is a question whether these that actually occur before, these resonances occur before you have a chance to have these macroscopic resonances also can trigger MBL some kind of instability. I don't think so, but maybe. And then the point is that there are a lot of very small scale numerical work which show a drifting transition point. So if you look at longer and longer scales, you see the transition drifting. I think there are actually, even within the theory that I'm going to discuss, there are good reasons to expect that. So I think David was talking about this kind of drift of the MBL transition, not due to the BAA versus these instabilities, but because basically these instabilities are get pushed to a much larger disorder strength than we naively would expect, because of other effects and so they're pushed in disorder strength, not in localization length, but in disorder strength. They're pushed somewhere here, and there is a region which looks like a crossover regime, and that crossover regime is so this is the reason is because when you're looking at too small a system, you think that the localization length is log 2, but the localization length is still flowing for some reason. I'll now show one reason why it can flow. Yeah, so beside this crossover, there is another one that David talked about, and I think this one is very well understood. So I think what I showed you now is basically kind of a good description of this crossover. But the description of this crossover, I think, is still an open question. You're muted, but
yeah, sounds good. Thank you.
Okay, thanks.
I have a question.
Sure.
So it seems like in the beginning of the lecture, you showed how just using Fermi's golden rule on like a system of size L gave us this criterion for the minimal localization length just being less than 1 over log 2.
Yes.
But then we got the same result using the avalanche instability, also gave us a 1 over log 2. So
right.
So why do we need? It seems like you would have gotten so why do we need these rare thermal regions? To begin with?
It's a very good question. Actually, I don't think we really need these rare thermal regions. I think basically because we have these rare thermal regions will just will just happen no matter what. The correct reason is, though, it's a very good question, but one way to rationalize this is the following. So To be more precise, I gave you a rough criterion because I mean, I didn't really do Fermi golden rule. I needed to go to very high order. Instead of going to high order, one can do something else. One can actually write down the Hamiltonian, this effective Hamiltonian of conserved quantities, and then ask whether it will be stable or not. But then by definition, it's stable because once it's just a unitary transformation compared to your to your original Hamiltonian. So now what do I mean by it being stable or unstable? Well, what it means is whether I didn't notice, but some of my conserved quantities actually have the length of the entire system, which I assumed they didn't. But to check this possibility, I needed to apply some other perturbation and check whether that perturbation can couple all states instead of couple just two states. So I need to apply some perturbation to my system, and one such perturbation could be a rare region. But you're right that these rare regions, in this case, they're it's not clear how important they are for destabilizing the system by itself is very, very fragile. Once we have basically have any the rare region size can be microscopic, and it will give you an entire instability. So which means it's probably not too crucial, but you need some in order to get something. You need some instability. Sorry, some seed to the instability, and these provide the seeds. And they are important to for this two-parameter scaling theory for what it's worth. So let me, since the more rigorous understanding of these instabilities does involve a rare region or some kind of seed perturbation, then let me stick with that and try to now leverage this insight into a scaling analysis. Okay, and this is taken from the paper by Dumitrescu and Romain Vasseur, Sid Parmassaran, and Maxime Serbin, and Serbin's student, I forgot her name. You can look at this. It's a very nice paper, and they basically give a phenomenological scaling theory for the transition. And the idea is, if the transition is driven by the avalanche instability, let's assume it is, then a minimal model of the transition has to include two variables. It has to include this inverse average localization length, this thing, because we know that this is what sets the instability. If it's below log 2, then it's stable, and it's unstable. If it's above log 2, it's unstable. And another thing is that we know that there are some thermal inclusions. There have to be some thermal inclusions, and having thermal inclusions in the system will renormalize this localization length. So if the microscopic localization length is something, if we add some thermal inclusions, it will renormalize this localization length upward, or it will take this inverse localization length down. So these are the two parameters. It's like a minimal change to our totally homogeneous system. We still assume that this density is homogeneous in the system. The localization length is homogeneous in the system, and the inhomogeneity is included by adding another parameter, which is the density of these thermal seeds. Okay, so and what is initially this at the microscopic scale, what are the localization length and what is the density of thermal regions is determined by microscopic parameters. So the disorder sets microscopic localization length, and it sets the probability of having regions of some size that are thermal in the thermal side, and so on. and we start from that, and then we rescale. And what we expect is two things to happen. So first, according to the avalanche criterion, when we rescale, if we find that the localization length at that scale is smaller, inverse localization length is smaller than log 2, then this density of thermal regions should become relevant and renormalize upward. This is one thing we know. Another thing we know is having some finite density of thermal regions should renormalize inverse localization length downward. Okay, so towards more localizing, more delocalizing. These are two things that any set of scaling equations should, with these two scaling variables, we're not guaranteed that this is enough, but it's a minimal model that goes beyond this uniform system. They have to satisfy this. And then what do we expect in the MBL and thermal fixed points? Well, in the MBL fixed point, we expect that there are no thermal inclusions at the fixed point. So rho is 0 when we go to the fixed point, because when we renormalize upward, any small thermal inclusion will be thermalized by its surroundings and will become thermal, right? So if we look at the larger scale, it doesn't look MBL anymore. Only if we look at it microscopically, it looks like a localized region. And what do we expect from the localization length? Well, the renormalized localization length must be larger than the critical localization length. Must be smaller than the critical localization length. Otherwise, we know it's not going to be a MBL. And in the thermal region, well, the density of thermal regions should go to 1 because everything is thermal. Okay, right. And the localization length is infinite, or inverse localization length is 0. Okay, so this is what we expect. So here are the simplest scaling equations that satisfy this. When I say simplest, I mean scaling equations at lowest order in rho. So first of all, we want, as we rescale, so log b, when I write log b here, this is log of the running cutoff A, the size, say, size of a unit cell over the microscopic unit cell A naught. This is log B. So the scaling equations d rho d log B have to make rho, we have to make rho grow when the localization length is larger, or inverse localization length is smaller than inverse psi c, the critical, and another thing is that when we have a finite rho, it has to make localization length, inverse localization length, renormalize downward, which is what we have here, right? So if it's 0, it's not renormalizing. If there is a finite value of rho, it causes to renormalization of size. So this is just the lowest order equations we can write down. Interestingly, they're completely equivalent. Yeah, I heard a question.
Just try to understand the logic. So on the previous slide, you had sort of postulated these fixed points and understood their renormalization properties on these arguments that you'd kind of presented before, you know, what happens with thermalizing regions. And so now you're just writing down what are the simplest flow equations that would be consistent with those fixed point properties.
Well, even not the fixed point properties, it's just these two, actually not the fixed points, but even just these two properties that, first of all, according to the avalanche criterion, if the localization length at that scale is smaller than log 2, then we know that rho is inverse localization length smaller than log 2, or in fact, this log 2, it should be log q, where q is the number of local degrees of freedom. But yeah, if it's smaller than that, then it should flow rho should flow up, right? And if it's larger than that, then the thermal regions win. Okay, so that that equation is basically just a statement of one, lowest order statement of one, right? That's it. And that as you renormalize, you look at larger scales and let things thermalize with each other, you see what used to be thermal regions get absorbed and become MBL. If you're satisfying the criterion that localization length is short enough, and the opposite happened, they start to avalanche if it's the other way around. And the second basically is just the simplest statement of the second of two, which is if you have some thermal regions, then even if they're irrelevant, they'll still renormalize your localization length and make it flow downward. So at lowest order, this happens just at first order in rho, and there is no reason why it will not happen in first order in rho. So there is some higher order terms which we can write down, but very close to the fixed point, which we believe is at rho equals 0. Because we're looking at an instability of the thermal region and in the, instability of the MBL phase. And in the MBL phase, by definition, rho is 0. That's why we are satisfied with lowest order in rho equations. Okay, and now if we stare at these equations, we see that they're completely equivalent to Kosterlitz-Thouless flow equations, well-known Kosterlitz-Thouless flow equations, by a simple change of variables. If I write y equals square root of rho, then we'll get y squared here, for example, y squared instead of this, and oops. And everything will look exactly the same as the Kosterlitz-Thouless flow equations. And then also the flow diagram will look a little bit more familiar, and it will have this sharp separatrix lines and then parabola around it that go below but I'm writing it in these variables, which are the physical variables here, and this is how the flow equation looks. And in this framework, you see that the MBL phase is a critical line in these allowed values of the localization length. And then there is a flow, relevant flow of rho beyond this fixed point. But you see also that if I undergo the transition, if I look at this transition, I will undergo the transition here, and the microscopic value of psi will not be the localization length, this universal value of localization length log 2 or log q, but it will be something different, and only if I look at sufficiently long times and long length scales, I'll see that actually I move down here. So as I go to larger and larger scales, I'll seem to see my my critical point drift. And my MBL phase will be, initially I'll see a much larger MBL phase than I expect to see. Then there really is. Okay, so I actually will see a drift already from this, and now it's not clear that there are no other reasons for the drift, and I think David wanted to try to nail down some other reasons for the drift, which I'm not sure are now still well understood. Now, to make the correspondence with Kosterlitz-Thouless transition a little bit, so the low T critical phase, which is, say, the more ordered phase, is actually here the MBL phase, right? It's a critical phase. You flow into it, and You can have various values of psi. So there is no one fixed point, but the whole line. What plays the role of vortex fugacity is, roughly speaking, the density of thermal inclusions. So in both cases, KT and this transition, you're talking about an instability of a critical phase to some kind of perturbation. In one case, the perturbation are creation of vortex anti-vortex pairs that then proliferate. And in the MBL phase, it's proliferation of thermal regions that become unstable at a particular point. So in that sense, it's indeed similar. And the stiffness constant in the KT transition becomes the inverse localization length here. And the universal jump in the stiffness, for those who know in the KT transition, is the universal jump in the inverse localization length from log 2 to 0. Right, and the inverse, and this, this universal jump actually depends on the number of local degrees of freedom. So it's basically log Q to 0 in this case. One shouldn't take the log 2 completely seriously.
Ehud?
Yeah.
What's the mapping? So what's the analog of the dynamic critical exponent in the MBL?
Yeah. So I don't. That's a very good question. And in so the KT transition and the flow lines here of the KT transition are not dynamical at all. So you don't really have the dynamics here. But there is, so to get this infinite Z transition, one needs to look at, yeah, so in the usual KT transition, I would say there is no analog. But there is actually an interesting analog if you look at a transition, KT-like transition in one dimension from disordered bosons in one dimension. So you can write down, for this, you can write down strong disorder. So one way to look at this transition at weak disorder will probably be discussed by Thierry Giamarchi next week. And that's a well-known paper by Giamarchi and Schultz for Anderson localization of interacting bosons or fermions in one dimension. And this happens at the universal value of the Lattinger parameter, and there is no diverging dynamical exponent there. The theory is not dynamical and so on. On the other hand, one can ask what happens if you have in one dimension and you have very strong disorder, you have the same kind of transition. And the point is that in one dimension, we know that strong disorder can create bottlenecks, which is something not taken into account in the usual Giamarchi and Schultz analysis. And it turns out that if you write down the strong disorder RG equation, so this is a paper by myself and I don't remember, and Gil Rafael. I'm not sure I remember the order correctly. Polkovnikov and Caffrey. In 2004, I think, Pierre Allen. And then there are several other follow-up papers. But the idea there is that you can actually do a strong disorder RG that is very similar to the RG scheme you have for the MBL phase, and you get a KT-like transition with exactly the same kind of flow equations. There it's more microscopic, and you see that what exactly this rho and psi correspond to. And in this RG, you can also compute dynamics, and you find that the dynamical critical exponent diverges at the transition. But again, it's completely dual to this, because the critical phase is, of course, the superfluid of the bosons, and you have an instability to a localized phase, and here it's the MBL phase, which is the critical phase. So it's not really analogous to that. It's not the MBL transition at all. It's transition in the ground state of bosons, but the dynamical exponent does diverge in exactly the same way as here. But in the usual KT transition, I don't think there is an analogy. What time is it? I might, yeah, so I might only have time to finish that first part on MBL, and
we should try to leave at the minimum sort of 5 minutes for questions at the end.
Okay. Yeah. So I'm done basically. So the next thing I can go through faster next time in half an hour or so. It's very short, and it's mainly related to one paper. I wanted to make some connection to open-driven systems, because you had a lot on open-driven systems, and it sounds a little weird how we can have any kind of interesting sharp signatures of MBL in an open system. So I'll leave you to think about that and talk about it next time. And in the second, then in the second half of the next lecture, I'll switch to dynamics of quantum information. But let me just, since I talked about this KT transition, just let me talk a little bit about what are the consequences of this, kind of maybe measurable consequences in some way. So we talked about these thermal inclusions inside the majority MBL phase. And we can ask, what is the distribution of their sizes? We saw that in the thermal phase, they had a specific distribution, that the MBL inclusions had a specific distribution. What is the distribution of these thermal inclusions in the MBL, at the critical point of the thermal inclusions at the critical point? Because remember, in this KT framework, the critical point is basically supposed to look more or less like the MBL phase. It's majority MBL, and it has some rare inclusions. That has to do with the very huge asymmetry between MBL and thermal. Thermal is always stable, but the MBL phase can be destabilized by a minute amount of thermal regions in it, right? So we can have basically a fractal dimension of some, not even a one-dimensional system of thermal regions, and that will be enough to destabilize the MBL phase. So we can ask a question: what is the average size of thermal inclusions, first of all? So according to our argument, remember about this avalanche argument that Grace correctly said, it's basically the same thing as the more, less sophisticated Fermi-Golden rule. According to this, you see that the behavior of this fact G parameter around the thermal region, it decays. As long as if you're in the MBL phase, it decays, but it decays not with the localization length, but with the corrected localization length, where the inverse localization length now is psi -1 minus psi c -1, right? So there is a corrected localization length. So we can maybe say that the thermal cluster is renormalized upward, and the size of the thermal cluster is now set by this length scale, right? Because this is the decay we have. So this looks like the size of a localized region, according to this. Now, according to microscopic RG scheme that I mentioned before. So basically, I think it was said by various RG papers, but we were probably the first paper that said that the distribution of thermal inclusions, we didn't say what is the power law, but at the critical point, we predicted some power. L to the minus alpha, and it was pretty hard to compute that power. And later on, Philip de Montresco used our scheme to actually compute that power and showed that it's actually 2. But this distribution of thermal regions is argued by more microscopic RJ schemes to be a power law, 1 over L to some alpha. But now we can actually determine this alpha. So let's calculate the average thermal size of thermal region. So we just do an average integral over all the possible L times 1 over L to the alpha. This is the average. Oops, what happened? And we get that it goes like 1 over alpha to the 1 over alpha minus 2, and diverges as we get to the critical point. It would diverge at the critical point like it diverges here exactly linearly with the tuning parameter if at the critical point alpha is equal to 2. So in order to match with our result 10, we need alpha equal to 2 at the critical point. And that will call it, will make it diverge. By the way, if at the critical point itself, if alpha equal 2, then there the average localization length diverges indeed, but it behaves like log of L. So the average localization length, not localization length, average thermal size of a thermal inclusion diverges and becomes log L. So it's not macroscopic yet. The system still looks like MBL, vast majority, but it still has diverging size of thermal clusters. Yeah, so these are the consequences. There is some argument, and it's not known what is the behavior of the distribution of thermal clusters and how we can even measure that inside the MBL phase. Whether it's still power law distribution or it's some stretched exponential distribution. So there are arguments about that. You can read the different arguments already in the first paper by Dumitrescu on this, and then there is more elaborate arguments in later paper by David Hughes and Morningstar. But it's still under debate, and it's part of this physics, which if I want to lay out an open question, I think we still don't understand well the MBL phase, which seems to be like a very simple phase, but it has interesting distribution of thermal regions inside it, and because of that, this gives rise to a spectral function which has a lot of low energy modes. Although we expect not to have low energy response in the MBL phase, we do have a low energy response because of these thermal regions inside the MBL phase, and possibly because of other resonances that we're not taking into account in this theory. And I think David tried to talk about a little bit in his talk. So I guess now there is some 5 minutes for questions, or hopefully.
Perfect. Yeah, thank you, Ehud. So this was a very informative first lecture, and please ask your questions.
I wanted to clarify something, I guess. When you showed that phase diagram, there was a BAA curve and this curve where,
Yeah.
I guess. Yeah, I was confused. The y-axis was U, which I guess was for a model where U is the interaction between fermions. Yes. I guess I don't have intuition what varies this localization length in terms of the parameters of my model. Like, what model are we talking about, and how do I see it varying?
Oh, okay. So the model I'm talking about is, so the H0 would be some, say, a model chain with hopping of fermions. This is H0 plus disorder, sorry. Okay, that would be H0, and we could have some extra And then H interaction would be some ij, uij, and uij are sufficiently short-ranged. C dagger I, C dagger C I, C dagger J, Cj, for example. That would be, and uij maybe is nearest neighbor plus maybe a little bit of next nearest neighbor. Okay,
So how does
that's
this
microscopic model?
And I guess how does this like psi or this localization length depend upon these parameters?
Right. So it's a perturbative. What we are interested in is very weak interaction. Okay. So at very weak interaction, the localization length is, say, almost independent of U. Okay. The localization length is simply set by the disorder strength mainly, because U is very small. So there might be some tiny correction to the localization length. But the main question, as long as the system remains localized. So the question is whether the system does remain localized or not. And when I talk about localization length here in this BAA argument, I do it in their terms. And in their terms, they look at the perturbation theory around the non-interacting system. So in the non-interacting system, when suppose I'm in infinite temperature, I have a matrix element U that takes me from my eigenstate into other eigenstates by creating these, particle hole pairs, or pairs of scattering a pair of particles, right, from one place to another. And but there are many ways to do it. So there are many channels I can do it, and the number of channels is the bandwidth, the total bandwidth over the level spacing. It's the number of particle hole excitations I can go to. So the matrix element in the Fermi golden rule is basically U times the number of final states I can go to. Okay, and then I can, in order to see if I have resonance, I need to look at this matrix element over the level spacing. That gives me the resonance condition. Okay, so U here is just perturbative. So all the eigenstates I'm looking at and localization length, which is part of the eigenstate properties, are all from the non-interacting system, which is set by the disorder strength. If there was no disorder, of course, the localization length would be infinite. And in the non-interacting system, the inverse localization length is sort of an indication of the disorder. And that's why initially I had 1 over psi here as my y-axis. Really my y-axis, and I think Leo had a correct comment that the y-axis really is disorder, and if you want, it's the bare localization. It's just the strength of the disorder. And this instability occurs at the point where the disorder is strong enough so that the non-interacting localization length is exactly log 2.
And if you didn't have disorder, say you had the linear potential or something, would these arguments still hold?
Oh, linear potential? No. I need, all these arguments are for random system. Okay, so linear potential is a really strange beast, of course, because it doesn't even have equilibrium state. It doesn't even in principle have an equilibrium state. Yeah, no, it's all for random system. I even say, a lot of the experiments are done with quasi-periodic systems, which are they're not periodic exactly, but they're deterministic. And many of the arguments I gave are only for random systems, but we believe, although I'm not sure how well it is understood, that there is also many-body localization for quasi-periodic systems in 1D. But then we can't use all the Griffith arguments for rare regions and all that, because there is no such thing in a quasi-periodic system. So everything I said now I have to reserve to just random disorder, and more than that, even uncorrelated or short-range correlated randomness.
So Jaren, did you have a question?
Hi. So my question is related to about this rare regions. I'm curious whether we could find this kind of rare regions and bottlenecks in quasi 1D systems, like ladder systems, for example.
In which systems again? Sorry.
Like quasi 1D, something between 2D and 1D, but like not exactly 1D. Like for example, a ladder system.
Ladders. Yeah, so anything that is finite in one dimension, in principle, is 1D as far as we're concerned, except that you can think about it as 1D with a large number of states per unit cell. So instead of log 2, it will have some log q, and it will be much harder to localize and so on. So, but I think it would still hold as 1D, as effectively 1D system.
Thank you.
Haltian?
Hi, yes, I have a question about the KT-like RG.
Yes.
Is there any kind of the essential singularities in the given the KT-like RG in the MBL transition? Will it bring any kind of the physical effect on the numerical or experimental observations?
Yeah, it's a good point. One thing it will probably say is that it'll be very hard to see this transition because of this essential singularity in KT transition. The finite size effects decay very slowly. They decay logarithmically with the system size only. So it's not usual finite size scaling with critical algebraic scaling. You have a very, very slow decay of finite size effects, which means it's always hard to see it's always hard to see the MBL. It's always hard to see KT physics and nail down that it's KT physics, and it's even harder here for two reasons. First of all, because there is no way to do simulations in sufficiently large systems, although I'll talk about one possibility next time. But there is another even more fundamental problem that you need to go to large, because of this KT physics and essential singularity in the localization, and the diverging length scale diverges exponentially, finite size effects decay logarithmically. On top of that, we have dynamical exponent z equals infinity. So what does this mean? So it's a very good question. So let me try to answer it. Did it put in a new page? Yeah. So so first of all, we need to go, because of KT, we need to go to very large system size to kind of nail down the effects, the finite size effects. But we also have z going to infinity, which is independent of this KT physics. As I answered to Kaden, KT physics doesn't immediately imply, of course, z infinity. So what this means is, at the critical point, tau goes like e to, this is z infinity, right? It goes like L to the infinity, and really it goes like e to the L, right? L over L naught. This is, we know that at the critical point, this system looks MBL, and you have exponential scaling of the time with the length, right? So we need to go to large length scales, and then in order to see finite size effects decay, and then we need to go, and But in order to go to these large length scales, we need to go to exponentially long times with these length scales. And that's why I think I've been kind of toying with the question, part seriously and part jokingly, whether MBL is even too hard for a quantum computer. Because all of this has nothing to do with our, we'll have to wait this long time. We'll have to go to these large systems. Where did it go? We'll have to go to these large systems in order to see finite size decay, even if we had a perfect quantum computer. And then in this quantum computer, to see true MBL physics at these scales, we'll need to go to this exponentially long length scales. Of course, we're not going to be at the critical point. We're going to approach it, but Z is going to diverge. As Z diverges, we're going to need to go to longer and longer times and eventually reach this exponentially long time. So it looks like there is a fundamental problem in seeing MBL physics because of these two things. One that you mentioned, that there is an essential singularity that leads to logarithmic decay of finite size effects. And then compounded on that is infinite Z, which means that we need to go to exponentially long times with these system sizes, which is probably even if we had a perfect quantum computer, will be well beyond the lifetime of a graduate student. So I wouldn't, raise my hopes for an experiment on that. Yeah, this is a problem, I think. Yeah.
So as so often happens, I think we need to cut off the discussion so we have time for a break before our next lecture. So in 20 minutes, we'll reconvene. Take all the questions that have built up here and bring them to Ehud's next lecture. We can start with any remaining questions. So thanks for the great talk, Ehud, and see you all soon.
Bye.